Assalamualaikum viewers, please like, share and subscribe this channel. Links of PDF files used in this video are given in description. So today's lecture is about structure of metal carbonyls, and this is a part 6 of this lecture series. And in this particular lecture we will discuss binuclear and polynuclear molecule examples such as Fe2CO9 and Fe3CO12. Now next example is enea-Carbonyl di-iron, and this is the overall geometry of this molecule. So again it contains two atoms of iron that are attached with each other. Each iron atom is attached with three carbonyls, both with A atom and B atom, and in this there are now total three bridging carbonyls. So again in the complex, if we see, there is no charge on the complex. Carbonyl is 0, iron is 0, so the atomic number of iron is 26. This is the valence shell configuration, and now this is the valence shell configuration written in the form of valence bond theory, which is 4s2 and 3d6. Now we see there are two iron atoms, and again odd even rule we will use. Again with each iron atom actually there are three carbonyls or odd number of carbonyls attached. So in 2 we will not show any back bonding, whereas in 1 we will show back bonding. So in both let's see, there these are the two carbonyls which exist in A form with no back bonding, whereas one carbonyl is attached with B form, which is B form for back bonding, and these are the electrons contributed by iron atom towards the back bonding carbonyl. So after these terminal carbonyls we have fixed, now there are three carbonyls that are bridging. So these are the three bridging carbonyls, and these are the electrons. Green are the electrons contributed by the carbonyl, whereas the red electrons are contributed by the metal. And in the last we will draw this metal sigma bond, which is represented by here, and then both contain one inert pair of electrons. And in order to make sure that all electrons have been included, so we will count them 1 2 3 4 5 6 7 8. So in this way there are total number of 8 electrons consumed, like this: 1 2 3 4 5 6 7 8. So all electrons have been included. So this is the overall bonding situation of enea-Carbonyl di-iron. Now next example is dodeca-Carbonyl tri-iron or Fe3CO12. So this is the actual geometry of this complex. Again now there are three iron atoms that have been attached with each other through metal sigma bonds, and with each iron atom, like with iron A and B, there are three carbonyl molecules attached. These carbonyls are called as terminal carbonyls, whereas with this third iron there are four carbonyls attached, whereas one carbonyl, there are two carbonyl bridges are present. So if we see in the previous geometry the structure of Fe2CO9, so this is the geometry of Fe2CO9. What is the difference between Fe2CO9 and Fe3CO12 is that if we remove this bridging carbonyl and in place of it attach the four carbonyls, so this is the exact geometry which is represented here, which is Fe3CO12. So it means Fe3CO12 can be found from the molecules of Fe2CO9. So let's focus on the geometry. So there are three iron atoms. So in bonding situation we also have to include these three iron atoms, but first let's focus on these two iron atoms. So again in the complex there is no charge on the complex. All 12 carbonyls are neutral, so all the iron atoms are neutral. So this is the iron, and this is its atomic number, and this is its valence shell configuration, which is 4s2 3d6. This is valence shell electronic configuration written in the form of valence bond theory. Now again we are going towards same odd even principle. As with each iron atom A and B there are odd number of carbonyls. So in two molecules there will be no back bonding, whereas in a single molecule we will do back bonding. So if we see here, these two are the molecules with A form with no back bonding, both are attached with iron A and iron B. So here there are also two molecules of carbonyl with A form and one molecule with B form, and in order to show back bonding from the metal, these are the metal electrons that are donated towards this carbonyl through pi bond. Similar is the case with the iron B atom. Now in between iron A and iron B there are two bridging carbonyls attached. So in these two bridging carbonyls, these are the electrons shared, where the red electrons are contributed by the iron, whereas the green cross electron is represented by the bridging carbonyl. And at the last, this metal bridge has been represented here by the overlap of iron-iron orbitals. Now the third iron, which contains four terminal carbonyls, it has been represented here. So this is iron C, this is its 3d orbital, this is its 4s, and this is its 4p. Now with this terminal iron C atom there are four, so it is or even number of carbonyls. So in two there will be back bonding and in two there will be no back bonding. So here with these two we have drawn with A form and there is no back bonding in these carbonyls. These are the electrons contributed by these metal carbonyls, whereas these two are with B form and these are with back bonding, and here comes the back bonding electrons. And in the last we have to attach this iron C with both iron A and iron B through metal sigma bond. So here with this single electron, this is overlapping with this electron. Similarly this unpaired electron is overlapping with this unpaired electron of iron A. So in this way two metal sigma bonds that are represented here are actually, these are the bonds which are represented here, whereas between iron A and iron B this metal sigma bond has been represented in the bonding situation, which is lying here in the geometry. And in the end all the three contains one electron pair which is remains inert. So in order to count or see that all the electrons have been included, so we will count the valence shell electrons 1 2 3 4 5 6 7 8. So in bonding situation we will see that all 8 are consumed. So here 1 2 3 4 5 6 7 8. Similar this situation with this. Now let's see with iron C, 1 2 3 4 5 6 7 8. So all the electrons have been satisfied and their pairing has been satisfied. So this was the geometry of Fe3CO12, which include bridging carbonyl. That means these molecule also showing IR peak at 1850 per centimeter. Now one main question is that we have made that this arrangement fixed. Like first we are dealing with A form carbonyls, then we are dealing with B form carbonyls, then we are dealing with bridging if there is some bridging, and then we are dealing with metal sigma bond, and in the last resort we have placed the inert electrons. So this arrangement can be shifted, like these back bonding carbonyl can be placed here and these A forms can be drawn later. Similarly these carbonyls can be drawn later and this metal bond can be formed in the place of bridging carbonyl. So there is no fixed arrangement, but we have make this arrangement fixed in all the geometries in order to have better understanding. So what we have done, that first we will draw any A forms of the carbonyl, then we will draw B forms of the carbonyl, then we will draw the electrons that are coming for back bonding. After then if there are bridging, then we will draw bridging carbonyls, and in the last we will draw metal sigma bond, and we have kept this arrangement fixed in all geometries. And in the last we will place the remaining inert electrons if there are present. So this was the geometry of Fe3CO12 molecule. Here is an other geometry of Fe3CO12, and in this geometry we are seeing that there is no bridging carbonyl present. So it means this geometry don't have any peak around 1850 per centimeter. So this is the possible arrangement in which there are three iron atoms that are attached with metal sigma bond, and with each iron atom there are four terminal carbonyls attached. So let's see the geometry of this shape of or this structure of Fe3CO12. So overall complex is 0. All the things will be same as compared to the previous complex. So this is iron 26, atomic number 4s23d6 is its electronic configuration, and this is valence shell electronic configuration written in the form of valence bond theory. Again, there are three iron atoms A, B and C. With each actually even number of carbonyls are attached. So with half we will do back bonding, and with other half we will never do back bonding. So here we can see among four, two are with A form and two are with B form, and here comes the back bonding electrons from the metal. Similar is the situation with iron B, with two with A form and two with B form, and these are the electrons that are coming from the metal to form the pi bond. Similar is the situation with iron C, as four are attached with, so two are with A form and two are with B form, and these are the pi bonding electrons. Now remaining what we have to do is we have to attach these through metal sigma bond. So let's see first this bond which is between iron A and iron B. It is represented here in the bonding situation. Then there is the sigma bond, metal sigma bond between iron A and iron C. So here is this bond represented, and then the third metal sigma bond which is drawn between iron B and iron C, which is represented here, which is metal sigma bond. Let's at the end count all the electrons in the metal. So 1 2 3 4 5 6 7 8 electrons, 1 2 3 4 5 6 7 8 in iron A, 8 in iron B, and 1 2 3 4 5 6 7 8 and 8 electrons are in iron C. So it means all the electrons have been adjusted. So this is the another isomeric form of the Fe3CO12. So at different temperature pressure conditions, this is another geometry which is not having any bridging carbonyl. So it means this complex don't have any peak around 1850 per centimeter, which is an indication that there is no bridging carbonyl. So this was all about today's lecture. I hope you students have well understood this lecture, but if still you have question in your mind or if you have some query, then please let me know in the comments. I will respond to your queries as soon as possible. So for the time being, okay, thank you. Allah Hafiz.